Bonjour. In this video, I'll briefly talk about my project on Nonequilibrium Molecular Dynamics simulations of heat transfer in magnetic hyperthermia, and I'll detail the current status of where we are at with this project. So, with the motivation for this project, studying local temperature is essential around nanoparticles that emit heat energy, because we want to know if injected nanoparticles in tumor tissues can kill the tumor tissues or not, or if they are surrounded by polymers which are temperature sensitive to release drugs, can they release that or not, and the efficiency of the process. So since local temperature is something we can't measure directly experimentally, we make use of simulations to understand if the processes are feasible. So the approach we take here is we collaborate with experimentalists who measure the global temperature of a magnetic hyperthermia process, and they calculate the specific absorption rate of the materials, that is amount of heat energy absorbed per mass of the material, unit mass of the material. We get the values from them, we get the data from them, we input that SAR values into our simulation as an internal heating of the nanoparticle, which can be done in both lamps and in normal heat simulations. We compare the simulated global data of the temperature that we simulate with the experimental data that was measured by the collaborators. We see where how closely these two are correlated with each other, and once we are sure about the correlation, we analyze the local temperature evolution in our simulations to know how the local temperature is evolving around the nanoparticle. So to recap what I did in IPCMS, the project involved solving heat equation using finite difference method for long time simulations. So we had the nanoparticle and water surrounding it. We had heat equation with certain boundary conditions, and we could simulate we could have a simulation time of around 80 seconds, which is close to what experimentalists have done in the experiment. And we have a good temperature profile of what is physically accurate for physically typical for a interface between nanoparticle and water. We also have a global temperature evolution that closely correlates to what was simulated. There are differences because we don't take into account secondary effects, heterogeneity of magnetic field. There are a lot of effects that affect the evolution of global temperature, which we don't take into account. But this is a good approximate starting point of trying to simulate magnetic hypothermia. So when this was transitioned into trying to simulate in MD, we were optimistic. At least I was optimistic, because I didn't know the sizes of the simulations that are feasible in MD. But when I tried to simulate the original systems, the time step that is needed to do an MD simulation is at least 1 femtosecond, and the fluctuations are so large in normal MD simulations of temperature that we at least need to simulate up to 1 millisecond to at least see an appreciable change in temperature at any point in the region, which takes a lot of time steps and is not feasible during this simulation. On top of during this internship, on top of that, the original system will be comprised of millions and millions of atoms, which are not lamps. Has to have a data file to include where we define the positions and velocities of the atoms that we want to simulate. With the current technology that we have to process these data files, we can't simulate systems this big. And there were some simulations that were done where they do exactly what we are trying to do, which is constantly heating nanoparticle and trying to simulate local temperature. But most of them use thermostating around the water for large spots of water, large regions of water. So they reach steady state really easily. We don't want to do that because as will be explained in a while, we are scaling down the system. So we need to have a hands-off as much as possible, hands-off approach. So to do this, what we are trying to essentially do is since we can't simulate local temperature around the nanoparticle for the accurate system for the entire system as a whole, what we are trying to do is we are trying to somehow get the value of G, that is which is interfacial thermal conductance. We are trying to get this value to then use this value as an accurate value for our FDM simulations that are written in IPCMS, and see if we can at least see some something that is meaningful in the results. So what we essentially try to do is, since we can't simulate that, we try to scale the systems down. So since the original system particle size was 8.5 nanometers, and the water box that we chosen according to the density was 127 nanometers, we had to scale down the system to different radii. We have chosen 0.85, 1.73, 1.5 nanometer radii for the nanoparticle. Choosing the size for the water box was tricky because there can be it depends on what we want to keep as a constant. We can scale down the dimension of water box according to the scaling down of the nanoparticles, or we can keep the concentration that the experimentalist used, which is 1 milligram of iron for 1 ml of water, and trying to get the total number of water molecules and then the density according to the density the box size. But in either of the cases, the number of water molecules far exceeds what can be done with the machine power that I currently have access to as a stagiaire, as an intern. The machine power I have access to is not enough to simulate these large systems. So even in the scaled down systems, we can't completely try to simulate. So we have to compromise even further. I'll come to what we have compromised as. So while searching the literature for magnetic hyperthermia simulations and calculation of G, I have read a lot of papers, probably around 15 to 20 papers, and the papers the work that is relevant to us can be broadly categorized into 3 different regimes that can be that are explained in a moment. So there is the first regime is layered approach, where we use a Muller-Platt type NEMD simulation. We have a constant heating at one point, and thermostating is really low. So it is in the regime that we want. We want to heat the nanoparticle, and we want to use as little as thermostat as possible. But the configuration of this system is not similar to what we are trying to simulate. These are layered structures, and we want to have a outward from the nanoparticle heat transfer that is not as similar to this. And since G, the interfacial thermal conductance, depends on the configuration and the shape and the size of the system that we are trying to simulate, we can take some positives and some points from these type of simulations and trying to include them in our simulation, which I will come back to. I'll come to things that we are trying to simulation. The second approach is the simulation that is configurations that are closest to simulation. We have a nanoparticle and water surrounding it. Heat is constantly put in the system, so the configuration is appropriate for our simulation. But the problem here, in most of the papers that I've read, is they have heavy thermostating, so they thermostat large portions of water around the nanoparticle, so they reach steady state really easily, and they calculate thermal conductance in this steady state, which is easier to calculate. We don't want this regime because we are already scaling down our system and even our scaled-down system of water boxes can't even function, so we are scaling down even more. So our system doesn't even close to resemble what our true system is. And if we are thermostating large swaths of this force system, there is a problem of falsifying the results. So we want to thermostat as little as possible, and these simulations also occur in really low time steps. We want to have a large simulation for a longer time. So these simulations are essentially have arbitrary energy values, arbitrary dimensions, everything are arbitrary. They are just trying to see how nanoparticle temperature evolves, but they are not correlating it with any experimental data, or anything like that. So there is some positive things that can be taken from this type of work, but it is very limited. Third thing that is normally done in magnetic, trying to simulate magnetic hyperthermia is really they scale up the system. So as you can see here, the particle sizes are really in millimeter. So they can accurately simulate what the experimentalists see in the time scale of seconds, because the particle sizes are in millimeters, and they are essentially doing is they are solving the heat equation in different tumor cells. So it's good that at least trying to correlate this with the experimental results that they have. They input the energy that experimentalists give them into the system. So it's not the energy values are not arbitrary that are input into the system, but the dimensions are not even close to what nanoparticle dimensions are. So there are some positive things that can be taken from the system, but it's limited to in our pursuit. Our goal is to simulate systems that are relevant to what our collaborators, experimentalists, gave as an experimental result. So these are some things that are not published. So what we want is our simulation should have characteristics of these three. We need to correlate our experimental our simulated results with experimental results. We need to have constant heating with very low thermostat, but the configuration is to be water surrounding a nanoparticle. So after a few articles that I have read, I could finalize it to three ways that I can calculate interfacial thermal conductance, which I can then use it to do finite difference method for larger systems. I understand that interfacial thermal conductance depends on the size, and it is something that we want to study. That's why we had different sizes to see how interfacial thermal conductance evolves. So in each size system, we try to measure interfacial thermal conductance in three ways. The first way is energy balance of the system, where we just have we just say the energy evolves this way, and if the energy goes out this way, the flux is equal to G into T, essentially G into delta T. But the flux here is measured in a certain way. So this is the time-dependent version of what was published in Rajapur et al., where it's the main reference for us, and this is the time-dependent version of that equation 1. The second way of calculating G is in lamps we can calculate flux. We can measure flux at each time step. So assuming collinearity, we can calculate G from this formula, which is time averaged over, like, it can be 0.1 picosecond, 0.2 picosecond. That's what normally done in Muller-Plath method. So that's something that we can do in lamps. And the third feature that lamps provides is calculating phonon dispersion and vibrational density of states. So this is a bit tough, because at every time step we need to solve this equation. But since lamps has Python interface, we can calculate it each time step. It takes a longer time. Our simulations might take longer, but this can be done. We can with diffuse mismatch model, we can try to calculate G. So the problems that we are first I'll try to say how summarize what we can do in LAMMPS. So LAMMPS provides computes like a heat flux that we can calculate, used to calculate heat flux, and fixes like fixed phonon, where we can calculate phonon dispersion, dynamical matrix, and dump-to windows for vibrational density of states. So it is possible to calculate interfacial thermal conductivity. The box size are manageable. So we want to have a hands-off approach as much as possible with very low thermostating. So that we have to also measure the box size, effect of size of the water box that can be had on G. The biggest problems that we had from this project, when this project started in February, was initialization and system definition. LAMMPS has a convoluted definition regime where data files can't easily be generated and easily be read. It's not really compatible with PDB and other molecular dynamics data files. So that was one thing which we faced trouble with. And currently, I don't know the reason why it's happening, but the system that I'm running on is running slower than what it used to run. So I have data files and I have input files that can be run for every for every size of the system, 0.85, 1.5 nanometer, every system size that we want to see. But since equilibration and system running is taking a long time currently, we are trying to see how we can fast forward the system. Before our discussion on Tuesday, I hope to have at least the data for TNEMD. It's currently running now in the 0.85 nanometer nanoparticle size. It's currently running now. I hope to have the results, but we can discuss about it on Tuesday. So thanks for your time. Let's meet on Tuesday.